This is with respect to the previous flipped classroom activity I had assigned you. Today I shall be explaining heap sort algorithm, which implements transform and conquer technique. Heap sort is another algorithm for sorting problem. In the transform and conquer, problem is solved by transformation to a simpler or more convenient instance of the same problem, that is instance simplification, to a different representation of the instance, that is representation change, to a different problem for which an algorithm is already available, that is problem reduction. Why do we need this new technique? Because most of the applications involve sorting and we need an efficient sorting algorithm. We have already seen that merge sort takes n log n comparisons, but it has an inefficiency where in each stage of recursion a copy operation is required. And in heap sort, before understanding what is heap sort, let us understand what a heap means. Heap is a nearly complete binary tree. Here we have an example. 8 is the root node and 7 and 4 are the child nodes. The heap is constructed such that the root node is always greater than its child node. So 8 is greater than 7 and 4, 7 is greater than 5 and 2. So heap is a binary tree which is filled in this order, and we have a, and in this case the root is maximum element of the heap. So this property is utilized for heap sort. So every step, delete the root node, which is the maximum element, add it to the sorted list, and then heapify the remaining elements in the tree. For implementation, we need array representation of the heap. A simple array representation of the heap happens to be like this. Every root node has its child node, left child and right child in even and odd position with respect to its position in the list. So here is an example. 16 happens to be in the first position of the list, and 14 is in the even position from 16, and 10 is in odd position from 16. Similarly, we have 8 in fourth position in the array, and 2 in even position with respect to 8, and 4 with respect to odd position 9. There are two kinds of heaps, maximum heap and minimum heap. If the root node is largest element, then it is maximum heap. If the root node is smallest element, then it is minimum heap. So if you want array to be in sorted or in descending order, then use maximum heap. If we want the array to be in descending order, then in ascending order, then use minimum heaps. A new node is inserted at the rightmost position. Is inserted at the rightmost position and deleted starting from right to left. For heap sort, we require these three operations: maximum heap, build a max heap, and then finally use these two property for heap sort. Maintaining the heap property. So every time a root node is deleted, compare it with its larger child, exchange it, and then move down the tree. Continue this until the node is not smaller than the children. So here is an example. So we have 14 which is smaller than its larger child node, so hence there has to be an exchange with this. So exchange 2 and 4. And now with this exchange, still we have violation in the property, so exchange 4 with its maximum heap, maximum child. So finally we have the heap property restored. In maximum heapify analysis, the time required for maximum heapify is log n, wherein log n is the height of the tree, and in each node in the height we make 2 comparison, hence it is 2h, and hence the running time is big O of log n. So the runtime for heapify is big of log n. To build a maximum heap, we need to perform this heapify. Just now previously we have discussed with heapifying with a single node. This has to be performed with n-1 levels. So hence I starts from n by 2 down to 1. So wherein we start heapifying with 1 level lesser than the leaf node. Here is an example. Let us consider 10 elements. So here is the binary tree constructed for the given list, and at the root node we have 4, and definitely 4 is not less than 16, so it violates the heap property. So hence start with the n by 2 with the root node at n by 2 position, where I is equal to 5. So 16 is compared with 7, there is no change. Now 2 is compared with I decrement I, 2 is compared with its larger child 14, and since it is lesser than, there is an exchange with 2 and 14. Now decrement I, and in the next level we have with I is equal to 3, element 3, which was exchanged with its larger child node, retaining the heapify property. Now I is decremented. Compare 1 with its larger child node 16, make an exchange, and now finally when I is equal to 4 we are arrived at the root node compared with the larger child 16, and there is an exchange. The resultant tree is a heap. Now this is utilized in heap sort. So first we need to build a maximum heap by heapifying n by 2 root nodes. So each heapify takes log n time, and this is performed n times. So hence the runtime running time is n log n. And these steps are used in heap sort. First build a maximum heap, then swap the root elements with the last element in the array, discard the last node by decreasing the heap size, call max heapify on the new root node. Repeat this process until only one node remains. So here is an example for heap sort. So we see a heap constructed here. First delete the root node, apply max heapify, and this is the resultant tree. 7 is deleted from the heap, added to the sorted list. Similarly, we heapify, delete 4, added to the sorted list, delete 3, added to the sorted list, delete 2, added to the sorted list. Finally 1 remains, and now the tree is empty. The resultant is a sorted list. Now analyzing the time complexity, this is the algorithm for heap sort. For I, starting from the root node down to 2, exchange the root node with ith node, apply max heapify, that is construct the heap back, and this is heapify takes log n times, and we perform deleting the root node n times, so it is n into log n, and this can be proved that it takes n log n time. Hence heap sort is better than merge sort.